last time we talked about what Q is and what Le Chatelier's principle is, and just the kind of theoretical aspects of which way will the reaction shift. Today we're going to look specifically at a mathematical problem that applies these things and how you might see this on, say, a free response. So what we talked about last time would be more applicable on a multiple choice. Will it shift the reactants or products, or there'll be more or less, increase or decrease? But here we'll look at some more numerical things. So in this example, we have a chemist who is mixing 80% of the N2 and 20% O2 in moles in a vacuum. And these are both gases. And when she does that, she then finds that the pressure is 1 for both of them. And she has this at a temperature of 25 degrees Celsius. And she knows the Kp value at 25 degrees Celsius is 1 times 10 to the negative 30th. So the first question is, what are the initial partial pressures of each gas? Well, that is going to depend on the percentage of each gas in the container. So we know that 80% of the gas is nitrogen and 20% is oxygen initially. And we also know that the pressure is 1 initially. So we'll use those two to find the partial pressure of each gas. So we'll take the total pressure, which is 1, and multiply that by 80%, or 0.8, for the nitrogen. So we know that the partial pressure of the nitrogen is 0.8. And we'll do the same for the oxygen. 1, that's the total, times the 20% that makes up the oxygen, and we get that it is 0.2. Notice that the pressure of the nitrogen and the pressure of the oxygen together add up to 1, which is your total pressure. So in terms of pressures, whatever percentage of something is in the sample, that is also the percentage of the pressure that it's going to make up. So there are our partial pressures for each of those initially. We don't have any nitrogen oxide or nitrogen monoxide, in the beginning. None of that has yet been produced. The next question is to find the equilibrium partial pressures at that temperature of 25 degrees Celsius. So we always need a rice or ice table, and we figured out our nitrogen and oxygen and NO initial values, so we'll plug those in on the I line. And then we'll go with our change line. So we're going to have negative x for our reactants, and then we'll have plus 2x for our product, because every time we use one of the nitrogen and one of the oxygen, we'll make 2 of the NOs. And we'll just pull those down to our change line. So our goal here is to find the equilibrium partial pressures for all 3 of those. So we need to figure out what x is. Right? So if you remember this from the first lesson, we'll write our K expression. We have a Kp value, so we're using pressures. Pressure of the NO squared, as its coefficient is 2. Pressure of the nitrogen and pressure of the oxygen in the denominator. So we have from our E line, if we're using K, we've got 2x, and then that's going to be squared. And then the 0.80 minus x and the 0.20 minus x. So we're just plugging those in. They gave us the Kp value, so we'll plug that in too. It was 1 times 10 to the negative 30th for our Kp. Now remember, when your Kp is less than 1 times 10 to the negative 4, we can avoid or ignore x's that are added or subtracted. So this negative x right here is going to be negated, and this negative x here, but we'll keep the numbers. So we multiply those together, and that's where the 0.16 comes from. Then up here on the top we had 2x squared, and remember that the 2x is in parentheses, so that becomes 4x squared. So then we're solving for x. That's going to be a simple cross multiplication, divide by 4, and then take your square root. So we get this as our value for x. Remember, our goal is to find the equilibrium concentration, or excuse me, the equilibrium pressure of these species. So we'll need to plug x back in to our E line. So for the NO, it was 2x. So we'll just multiply that by 2. For the N2 and the O2, it was those values that we had, 0.8 and 0.2 minus x. But if you put that in your calculator, you'll see that our x is so tiny, 10 to the negative 16th power, that it does not affect our nitrogen and oxygen in terms of significant figures. So those basically stay the same, and then we have an NO concentration now of 4 times 10 to the negative 16th. All right, what if we increase the temperature now? So I think they said the temperature is going to be like 2,000 something, and notice that we have a higher Kp value. So let's pause for a second and think about what happened here. So the temperature went up. What happened to the K value when the temperature went up? Well, in this case, the K value went up as well. Notice that it was 10 to the negative 30th, I believe, and now it's 0.0025. So that's a big change in our K value when the temperature went up. This K being much bigger than 10 to the negative 30th means I have more products. So when the temperature went up, that caused me to make more products. So where must the heat be in this reaction? Well, if the temperature went up and I made more products, then heat must be a reactant, right? Because if heat's a reactant, when the temperature goes up, I shift toward the products, and that makes my K value go up. If you'll remember on the summary from the last video, we talked about how if K goes up, that's favoring, when the heat goes up, you're favoring endothermic reactions. And so in this case, the heat went up and our K value went up, and so we know we have an endothermic reaction. All right, so moving on from there, we're trying to find the partial pressure when Kp equals 0.0025. So we'll fill in our ice table, starting with the same initial conditions, 0.8, 0.2, and 0. Same change in terms of x, so we have the same table. The difference here, though, is that we have a different K value. So we still have the same Kp expression. We still have the same x's to plug in, and we still have the same setup. However, we've got some differences here. Our K value is no longer less than 1 times 10 to the negative 4. In fact, it's greater than that. So we cannot ignore these x's. So we'll have to FOIL this on the bottom, and we'll get this expression here. We'll still cross multiply, and we'll get this that you see here. And then we will combine like terms, so we'll move the 4x over there, and we'll get this at the bottom set equal to 0, so that we can then apply the quadratic formula. Now, the AP exam does not require the use of the quadratic formula, but I wanted to give you a heads up that you may see this on homework sometimes, where we cannot use that technique where we get rid of x's. So your K has to be less than 1 times 10 to the negative 4th, and it wasn't here. We're going to let them do the difficult math here. I'm never going to test you on use of the quadratic formula because the AP exam doesn't either. Okay, so we won't spend our time there, but just a heads up, you could see it on the homework. So they apply the quadratic there and solve for x. Okay, so here's what they get for their x value. Now, remember that when you use the quadratic, you get a positive or a negative answer. Well, we're not going to have a negative x, right? So this is out. So here is our x value based on the quadratic formula. Online you can Google like a quadratic solver, and that's fine to use if something comes up on homework where you need the quadratic equation. But you want to take the positive root, not the negative one. Alright, so we know what x is now, so we can plug that in. We have 2x for our NO, and we see that's 1.9 times 10 to the negative 2. And then for our N2 and our O2, this time the x is affecting their value. So when we subtract that x from the N2, it's now 0.79, and the O2 is now 0.19. Alright, so all we did in those two examples is we used our rice table, plugged into K, and they were just different because one required the quadratic and one didn't, and they had different K values because the temperature changed. So an important note there, the temperature is the only thing that can affect our K value. And it can make the K go up or down. It just depends on if the reaction is endothermic or exothermic, and if the temperature is going up or if it's going down. So remember, ask yourself, where's the heat? Because they're going to ask you in some way, shape, or form that similar question. All right, so what can we do to change the K value? Remember, the temperature will change the K value, but we can also kind of manipulate the equation, and that will change the K value as well. So there are 3 ways in which K and Q can be manipulated. One is called the reciprocal rule, and the second is the multi-equilibrium, and then the third one is the coefficient. And that's the one that's not covered here, and so I'll hit on that one at the end. Alright, so the first one is the reciprocal rule. And what this reciprocal rule says is that if you have a reaction and you reverse it, the new K value is the inverse or the reciprocal of the old K value. And the same thing applies to Q. If you have a Q value and you reverse the reaction, then the new Q value is the inverse of the old one. So you can see that here in this example. Here is our original reaction that we made up, and here's the K expression. Products over reactants raised to their coefficient. Now let's say we flip the reaction around, which you see down here, and K is products over reactants raised to their coefficient. Notice this is simply the inverse of that. Alright, so your new K, which they signify by this double I, is your old K under 1. So 1 divided by your old K, or your old K raised to the negative 1 power. So it is the inverse, or the reciprocal. It is not your old K negative. Okay, so that's a common mistake. Like if your old K was 0.0025 and you flip it, your new K is not negative 0.0025. Okay, it's 1 divided by 0.0025, or 0.0025 to the negative 1 power. The reciprocal. So if you flip the reaction, your K value is the reciprocal of your old K value. If you have 2 reactions and you put them together, this is similar to whose law? Hess's law from thermo. Remember, we had to put the reactions together to make our goal reaction. This is very similar. So let's say you have 2 reactions. You got reaction 1 and what they're calling reaction 3. And we put them together to make reaction 4. What happens to their K values to make the new K value? Well, let's look. Here's reaction 1. Here's reaction 2. Products over reactants raised to their coefficient. Here's reaction 4. Or excuse me, 1, 3, and 4. Notice that for reaction 4, which is the combination of 1 and 3, its K value is the multiple of 1 and 3. So you do not add the K values together like you would in Hess's law. You multiply the K values. So when 2 or more reactions are combined, it's the product of their K values from the reactions. All right, the last thing that can happen, I'm going to back up a slide to give you an example, is you can change the coefficients on a reaction. So here, instead of 2A and 1B and 6D, we could have a multiple of that. So 4 and 2 and 12. All right, and what would that look like as a K expression? Well, that would be D raised to the 12th power, and A raised to the 4th, and B raised to the 2nd. Alright, so if you change your coefficients, in this case we multiplied our coefficients by 2, that actually changes your exponents by a factor of 2. So when you change your coefficients, if you multiply them by some factor, you raise your k to that power. Okay, so that's the difference there. If you multiply your coefficients, then you're going to raise your k to that power. So the coefficients become the exponents. Okay, you don't multiply your k values unless you're putting two reactions together. If you change your coefficients, you raise k to that power. All right, so that's the three changes that we can make, and that's how they affect k and also how they would affect q.